I was thinking that if the other person chooses to steal,
Mhm.
it doesn't matter whether I choose steal or choose split. I don't get nothing.
Yes.
So
it's slightly different to the prisoner's dilemma. Is that what you were going to say? Yeah.
so here it's better to like choose split because there is a probability that the other person does not choose steal.
Exactly. So if you were to look at the payoff matrix for this, it is a little bit different. If we call this player A and B, and we've got split or steal. And suppose our pot of money is M, then here you'd have M over 2. If you play steal and they play steal, you get 0. If you play split and they stay steal, you get 0. And if you steal and they split, you get M. So this is a little bit different from the prisoner's dilemma. It's the same main principle, but really, yeah, the optimal thing to do is here to steal, because if they split, then you should always steal. But if you're able to collaborate in some way, then it could potentially alter your outcomes. And that's the kind of similarity to the prisoner's dilemma. The classic prisoner's dilemma is that they're completely separated and they can't communicate with each other. One of the things that goes on in biological populations, say males and females, is they can signal to each other their intentions. So, and then it comes into a question of, are your intentions honest? Or is the signal that you're giving out an honest signal? That comes into, the genetic level, it comes into ideas then about linkage. So we talked about linkage disequilibrium, and this is all about when certain alleles or genes are more likely to be associated with each other than you'd expect by random. When you have that kind of linkage, that can maybe help tie together ideas about, is your signal honest and is your trait of altruism together? So that if they're close together, they're more likely to appear together, and therefore your signal might be honest. It's a little bit beyond some of the things we've been doing lately, but the point is that honest signaling becomes very important whenever there's a chance of communicating your intentions. Yeah.
When you're talking about signaling and like in our last about hawks and doves, do you mean signaling is like hawks signal with each other and doves signal each other, or hawks and doves can also signal?
I'm talking the hawk dove game. I guess you could signal in the hawk dove game, are you going to attack or not? But then there's a question: is that an honest signal that you are attacking? It's kind of related, but the ideas about honest signaling are slightly more about, yeah. I mean, ultimately, it's all about whether your intentions that you're displaying, whatever those happen to be, are true or not, or whether you're bluffing. So there is a similarity there in terms of the doves display, but they're just bluffing essentially. And in some sense, that's not a true signal. But the dove strategy could also be sort of, I'm willing to share this, rather than actually displaying. Okay, let's move on, because we should try and cover some stuff today, some actual math. So today we're going to be talking about evolutionarily stable strategies. Yeah, you don't have to stay sitting next to the person if I don't want you guys to overly socialize. It's fine. Okay, so yeah, the other day we talked a little bit about optimal strategies. We talked about this hawk-dove game as well as the prisoner's dilemma that we've just been through now. We're going to be talking a bit today about ideas around optimal strategies, and in particular the idea of an evolutionarily stable strategy, or ESS. We'll be coming back to this idea of an ESS many times throughout the course, so definitely pay attention to that. We'll also be talking about Nash equilibria, which are related to ESSs, but not quite the same thing. So yeah, we'll talk about Nash equilibria, these ESSs, other concepts today, the support of a strategy, and also the idea of a repeated game. So what you've just done now is just one game, one round of a game, but you can imagine what happens if you play the game against your opponent over and over and over again. That might alter your strategy because there's a possibility there for things like punishment. Okay, so let's just go back to the hawk-dove game for a second here. So this was what was introduced in the last lecture. Remember, the hawk and the dove are, these are just strategies. They're not actual hawks and doves. In this particular example, we can just think of them as being heritable strategies. So there's one population. Individuals can play with a certain probability distribution, any combination of these strategies. And we want to see, what is the optimal probability distribution. That probability distribution might ultimately be just play this one strategy all the time, or it might be some combination of those strategies. Okay, so our hawks contest for our resource, but potentially get injured. Whereas our doves display, they bluff, but then they retreat if they get attacked. And we talked about this payoff matrix for some values B, which is the benefit of that resource, and C, which is the cost of getting injured. We have this payoff matrix A, where Aij is the payoff to individual playing strategy I against someone who's playing strategy J. So this is your average payoff that you get. And in this matrix here, we've got hawks and doves. I'm just going to write H's and D's here to indicate those hawks and doves. So if a hawk and hawk play each other, they've got a 50-50 chance of getting the resource. But on average, they will also get injured as well with the cost of C. So that average payoff is going to be a half times by B minus C. If a hawk encounters a dove, then the hawk gets the benefit B, they get the whole resource, the dove gets nothing. And if there are two doves, there's a 50-50 chance that one of the doves will just back down. They're never going to fight over it, but one of them wins and one of them loses. So on average, they get B over 2. And we showed that if B is greater than C, then the hawk is always the best strategy. And if B is less than C, then the two strategies can coexist at some probability distribution, which we found was actually P star is equal to B over C. And this P star was the frequency of the hawk strategy. So this is how often the hawk strategy would be played. And in that case, every individual could be playing that hawk strategy, but just with probability B over C every time. Okay. So in general, we want to know which strategy is optimal in any given game and under a given set of conditions. So one thing we can do in game theory is to identify things called Nash equilibria. And these are named after John Nash, who pioneered game theory. Again, game theory really started out as thinking about human behaviors, especially in like an economic sense, but also in things like a military sense. And a Nash equilibrium is a situation where individuals who switch to a different strategy cannot increase their payoff. Okay, so you're playing a particular strategy. If you switch to a different strategy and you can increase your payoff, then it's not a Nash equilibrium. If you can increase your payoff, if you can't increase your payoff, then it is a Nash equilibrium. So based on our payoff matrix that we had before, a Nash equilibrium has to satisfy a strategy playing against itself, A of I against I. It's got to be greater than or equal to A of J against I. And this is true for all J. I've got there for all J not equal to I in my notes, but it's actually for all J. Okay, it's a pretty simple condition. You just have the highest payoff. So we can see here, for example, if B is greater than C, if you play hawk, for example, highlight it a sec. There we go. Okay, if you're playing hawk and B is greater than C, you can't increase your payoff by switching to play dove because B is greater than C. So this is positive and this is 0. So that would be a Nash equilibrium. And if you're playing dove down here, if you're playing dove, then, if your opponent is playing dove, then what should you do? Well, you could switch to being hawk. So that's not going to ever be, the doves by itself is never going to be a Nash equilibrium. Okay, because you can always switch strategy. Okay, the other way of thinking about this is a Nash equilibrium is just a case where a strategy where there is no better response to itself. Okay, so that's all to say the same things. Now, there's a slight variation on this. If we actually have a strict inequality so that AII is strictly greater than AIJ, or AJI, sorry. And this now is for all J not equal to I. Then this is a strict Nash equilibrium. In other words, it's the unique best response to itself. Not only can you not switch strategies and increase your payoff, you can't switch strategies and have the same payoff. So in this case up here, if this was an equal sign, if there was some other strategy that you could switch to that would have the same payoff, you've still not been able to better it, but there is some other response that could also be as good. And that gives you a weak Nash equilibrium, whereas the condition above gives you a strict Nash equilibrium. So question, can a mixed strategy be a strict Nash equilibrium? No. Why not?
as counter strategies? So it's like their other optimal options.
Yeah, so if you have a mixed strategy, then that is the one way of looking at it is this probability distribution. The other is that there is another set of individuals in the population who always play that strategy, and you're just defined by the frequencies of those strategies. So in that sense, more than one strategy will have the same payoff. So no, more than one strategy has the same payoff. Okay. So what about an evolutionarily stable strategy then, or an ESS? So an ESS is a Nash equilibrium, but it just has one additional condition. We have that the payoff for I against J, some other strategy J, is greater than the payoff of that strategy against itself, strategy J. This is true for all J not equal to I. So to note that if I is a strict Nash equilibrium, then this condition is automatically satisfied. It's the best thing against itself. And it's the best thing against anything else. So when I plays against J, this is going to be better than J against J. So what does this additional condition imply for a strategy that is a weak Nash equilibrium? And the hint here is to consider the case when strategy J is rare. What does this condition tell us? So imagine we've got a population that is just composed of one strategy, strategy I here. And everyone is playing that strategy. It could be a mixed strategy. It could be a pure strategy. It doesn't matter. But suppose then we have some other strategy, which is a mutation, a rare mutation, or some immigration event where something new comes into the population. I want to see whether that new thing can invade and replace what is currently there. Okay, so the question here is saying, okay, well, how does that strategy do against itself, this new thing that's coming in J? If it doesn't do very well, if it does worse than the thing that's currently dominant in the population, then it's not going to be able to spread. If it does better, then it is going to be able to spread. So this is telling you something about whether a rare thing in the population can invade. Okay, so this is basically saying if J is as good, so remember a weak Nash equilibrium, we're saying that J is as good as I. So it's, I'll just write it out again. A weak Nash equilibrium, we're going to have AII is equal to A JI. So if J is as good a response to I as I is to itself, then our additional condition requires I to be a better response to J than J is. What does this mean? Well, this means what I just said. This means J cannot invade. When rare. When we go on to the section of the course about adaptive dynamics, which is related to game theory, adaptive dynamics is also known as evolutionary invasion analysis. It's all about understanding this process of invasion and replacement. Okay. One way you can think about these payoffs or fitnesses is you can think of the fitness as being like a mountain. Okay. And the peak of the mountain is your ESS. That's your highest level of fitness. The question here is saying, is there another mountain peak that is as high? What we're also saying here is, can you actually invade? Can this rare strategy is as good, has that same height as your current peak, can actually invade? Okay, so last time we drew some graphs to think about how fitness varied with the frequency of a particular strategy. So what I want to do is just illustrate this distinction between Nash equilibria and ESSs using the same kind of ideas. So imagine if we've got the frequency of strategy I increasing, and we've got fitness. Okay, and we look at the fitness of two different types in two scenarios. Okay, so suppose, let's call it let's go for red. Suppose the fitness of strategy J decreases like this in our first scenario, and the fitness of strategy I decreases like that. So we'll call this WI and this WJ. So the first question is strategy I a Nash equilibrium from this graph? Why isn't it a Nash equilibrium?
Because if everyone plays J, then we have higher fitness.
So J is this one here, and I is this one here. Yeah.
So if everyone plays I, then the frequency of I is 1, and
Yeah.
the fitness is right there.
Yeah.
And if everyone plays J, it means that frequency of I is 0 and it's there and it has higher fitness.
But I has higher fitness here.
J has higher fitness as well.
No, but the key thing is the relative fitness. So the key thing is whether I is greater than J. So you remember our condition up here for a Nash equilibrium is whether, here we're talking about payoffs, but we're translating this to the idea of fitness because we're talking about evolution. The fitness, in this case, of strategy I has to be greater than or equal to the fitness of strategy J for all of our strategies. And in this case, this is for all frequencies of those strategies. So in this case here, this is a Nash equilibrium, right? Because this fitness is always greater than or equal to this one here. Okay, so it is a Nash equilibrium, but the question is then, is it an ESS? Well, for it to be an ESS, we need to have the fitness of this I to be strictly greater than J when J is very, very rare. And here it's not, they're equal. Okay, so this is a weak Nash equilibrium. I is a weak Nash equilibrium, which I'll just abbreviate to NE. Oh, sorry, I've made a mistake. I've got these around the wrong way. This is an ESS. Sorry, I've drawn my graphs the wrong way around. Apologies, this is an ESS. This is a weak Nash equilibrium and is an ESS. My apologies, I was getting ahead of myself and thinking about the next graph. This is an ESS because when J is rare, as J tries to invade, even though they're equal here, as soon as you deviate slightly away from 1 here, I is strictly greater than J. So they intersect at 1. So apologies for the confusion there. These lines here intersect at 1. As soon as you move ever so slightly away, so there's a tiny bit of this strategy J in the population, this red line is strictly below this green line. And therefore, it can't invade. So my apologies for the confusion there. It might become a little bit clearer if I switch these lines around and compare to what happens if we have this scenario. Make sure these lines sync up. Okay, if we flip these lines around now, and we have this scenario. This value over here is a Nash equilibrium. At p is equal to 1, if this our frequency of I we call p, is actually a Nash equilibrium. Because they have, at this point, it is better than all other strategies. However, as soon as this J strategy starts to invade, it has higher fitness, and so it can invade. Okay, so here, if you remember, maybe the easier way of thinking about this is the idea of a resident population and a rare mutant. So really what we're starting at this point, this yellow dash, yellow highlighted bits here, okay? So ignore everything else to the left of these curves for now. You start off here. Both of these cases are weak Nash equilibria because I is the best response to itself and there's no better response to it. Okay, so I and J have the same fitness here when we just have I in the population. And if you think about a slight deviation from that, we can approximate it as being at this point here. That's the same in both of these cases, but on the left-hand side, as soon as we have J trying to invade, it has a lower fitness. So as soon as we get pushed away from this point here where P is equal to 1, then Wj is less than Wi, so we get pulled back towards it, essentially. You can't move away from it. So this is an ESS. Whereas over here, as soon as you move a tiny bit away, even though they have the same fitness when P is equal to 1, J has higher fitness, so it can invade. Okay, so it is a Nash equilibrium because they have equal fitness, but it's not an ESS. So this is not an ESS. Okay, this is again a weak Nash equilibrium. So it's pretty easy to identify pure strategy ESSs from a payoff matrix. Because a pure strategy I is going to be an ESS if no other strategy can invade when rare. So the largest value in the ith column of our payoff matrix must therefore be the payoff against itself. So think about this question below. Which strategy in the following matrix is a pure strategy ESS? And is this a strong or weak Nash equilibrium? Well, suppose we've got a matrix A. Here I'm going to do a 3x3 game. Suppose we've got -1, 0, 3, 0, 1, 4, 2, -2, and 2. Okay, so which strategy in this matrix is a pure strategy ESS? Strategy 1, 2, or 3? Strategy 2, why? No, carry on. No? I mean, you had the right answer. So that if we look in the ith column, so first of all, let's look in the first column. So if we're looking about the statement here is saying that when we look in the ith column, the entry on the main diagonal has to be the highest entry in that column. Okay, so if we look in this column, for example, column 1, the ith entry is -1. But 2 here is higher. So this can't be an ESS because there is a higher value in this column. So strategy 1 cannot be an ESS. If we look at strategy 3, along the main diagonal, 2 is the payoff here, but there's a higher payoff if we were to switch to a different strategy. And then if we look in the middle column, the highest payoff is on the main diagonal. So this is an ESS. So it's a really nice, simple way of just looking at a payoff matrix to figure out whether we have a pure strategy ESS. In this case, strategy 2. Yes, sure.
In pair conflicts, Aij means that I play I and the opponent is playing J, right?
Mhm.
And it's the value of it is the thing that I get, my payoff.
Yes.
So if I say AII should be greater than AIJ, means that if the opponent is going to change its strategy, my payoff should not decrease.
Yes.
So, but we can look at it the other way around, that if I change my strategy
Mhm.
and the opponent doesn't, then my payoff shouldn't increase again. I think.
Depends what your opponent's playing. Is the opponent playing the same strategy as you to start with?
Yes.
Okay.
So I think that this should be included, because in the way that we're written is that individuals who switch to a different strategy cannot increase their payoff. So
Yes.
if I try to switch my strategy,
Yeah.
I should compare AII with AJI as well. The meaning of this sentence is comparing AII with AJI.
Yes. So that's what we have up here.
But
AII is comparing with AJI. Yeah.
so AJI,
So that would be me changing my row. So that's just like here. If AII, if I is equal to 2 is here, is this payoff here
but
1?
if the opponent changes its strategy and then my payoff decrease, I think this.
If your opponent changes, but
I think this is a bad thing again. It's a question about definition of Nash equilibria.
it depends. Well, it depends on the frequency of that opponent changing, right? Because we're talking about ultimately like populations here. So if your opponent changes strategy, well, if it's just one opponent changing, then you can't, like, they're not going to have a big effect. So the one way to think about this that we'll get onto at some point later is ideas of local stability, right? So this is equivalent in some sense to local stability. You're familiar with that, right? So you can think of there being a key issue in local stability. Let me sketch it on here. If anyone's, this is a slight aside, but when we're thinking about dynamical systems, for example, suppose you want to, the equivalent here is you want to get to a fitness peak, okay? So you might be at this fitness peak here, but there's a globally optimal one up here. So this is still an ESS. When we come to this, this is an ESS. This is also an ESS, but you can't just jump from this one here to here. Okay, you would have to sort of decrease your fitness and go through them. So ideas about ESSs are often also tied in with ideas about local stability. Okay, so if you like perturb the system greatly and everyone else shifts to the other strategy, then yes, you can switch to something that has a higher fitness, or your fitness might also, you could shift from this one down to here, right? So I see what you're saying, but this is all about making essentially like slight changes rather than everyone wholesale shifting, because this is not the biggest payoff, but this is the biggest payoff for an individual against itself, which can't, where other strategies don't have a higher payoff, right? So you know, this is the highest payoff here, but if everyone switches to strategy 3, then we have this issue of moving away from it, right? Some of these concepts around evolutionary stability are kind of like tricky to get your head around. Wait until we get on to things about evolutionary branching, because then you're talking about walking through landscapes that are changing as you walk through them. But yeah, the main thing I guess to think about this with Nash equilibria is that, or the distinction between Nash equilibria and evolutionary stable strategies is Nash equilibria are almost like an evolutionary stable strategy, but don't have this condition about invasion. So something rare can't invade. Okay. So, let's see what time we're doing okay for time. So what if no strategy is better against I than itself, but at least one other strategy is equally as good? So this is our weak Nash equilibrium, essentially. This means that some elements in column I are the same as in column AII, or sorry, as the same as entry AII, but that none are greater. So for example, if we change that matrix that we had before, now we have something that looks like this. So if we suppose that AII is equal to AIJ for some J not in I, not equal to I, so before our strategy 2 was our Nash equilibrium, but I've changed this entry up here now. So this is greater than or equal to the other entries in the same column. So A22 is greater than or equal to the other entries in the second column, but is not strictly greater than them. Okay, so we know that we can't be in a strict Nash equilibrium here, but we could be in a weak Nash equilibrium. So in this case, what do we need to do? We need to check whether I does better than J does against itself. This is this invasion criteria, right? So does this matrix above contain a pure strategy ESS? I've already answered, is this a strong or weak Nash equilibrium? It's a weak Nash equilibrium. But maybe spend a minute chatting to your neighbor and decide whether strategy 2 is a pure strategy ESS. Okay, what do we think? Show of hands, who thinks that this isn't an ESS? You know, who thinks it is an ESS? And who's not sure? Okay, let's go through this condition then. So the first thing, if we just go back to this matrix here, the first thing we can do is just look at any of our columns, right? And then we want to see, is that entry on the diagonal in that column strictly greater than all the others? If so, it is a strong Nash equilibrium. In this case here, if we look at our second column, there's an entry that is equal to the one that's on the main diagonal. There's nothing greater. So it's going to be a weak Nash equilibrium. And then if you recall, if we just go back up here a second, that we have this additional condition to check in the case of a weak Nash equilibrium. I refer to it as a strong Nash equilibrium. Usually referred to as a strict Nash equilibrium. If we've got a weak Nash equilibrium, then we can check this condition here. So the entry on our diagonal. So we're in column 2, and we want to compare the entry that is equal to the one that's in entry 2.2. So we have this additional condition here that we're checking. We're checking that for all other entries in this column, that our entry on the main diagonal is higher than that entry against itself, which is slightly confusing. So what do we have? Well, here, entry A row 1 column 2 is equal to entry A22. We can also say that A22 is greater than or equal to a J2 for all J. So the second condition here is for our Nash equilibrium, and this is telling us that it's a weak Nash equilibrium. Now we need to check whether AJJ is less than AIJ. So check if AJJ is less than AIJ. In other words, is J a worse response to itself than I is to J? And this is our invasion criteria. So this is saying that this strategy J, while it might be as good as I, it can't invade. So we look at AII. So in this case, sorry, AJJ, A and J in this case is 1. It's -1. How does that compare? Well, A21 is 0. So just to write this out, A11 is equal to -1. So here are, I'll just put in brackets here. Our J is equal to 1 here. And our I is equal to 2. So if we look at AIJ, we're going to be looking at A21, which is equal to 0. A21 is therefore greater than A11. And so I equals 2 is a pure strategy ESS. We don't have to be a strict Nash equilibrium to have an ESS. We can have a weak Nash equilibrium like this. All we need to do is check how that strategy that is as good as our best response performs when it's rare. That's Martha.
Sorry, I'm just a little confused. We're checking the condition on slide 6.
We are checking. Yes.
So on there, it's written as AIJ greater than AJI.
Oh, sorry, that is a J, but my writing is terrible, so that is a J there.
Shouldn't we check this for all J's? We only check for J equals to 1. If we check for J equals to 3, then the C doesn't satisfy that.
So this only matters for, so for J is equal to 3.
Then we should compare 4 with 2. A23 is 4, but A33 is 2, and it's
But we already know that this isn't a Nash equilibrium. We already know that strategy 3 isn't a Nash equilibrium, right?
yeah, but for the definition says for every J not equal to I, this inequality should satisfy.
So you're saying we should be checking it for
J equals to 1 and J equals to 3.
J is equal to 1, J is equal to 3. So
It's satisfied for J equals to 1, but it's not satisfied for J equals to 3.
let's see. It is, so if we switch, if J is equal to 3, just make sure I'm on the same page as you, then our A33 is going to equal 2, but our A23 is equal to 4, which is greater than 2. So strategy 2, yeah?
I switched the inequality, so I guess it's great, but we should check for this one as well. It does satisfy for that.
Yeah, it satisfies that, yeah. Okay. Okay, so that's pure strategies. What I'm going to do is, tell you what, let's have a break there. I'll allow you to eat your sweets, and then we'll come back and we'll talk about mixed strategies, and then we'll talk about some repeated games as well. Okay, so have a break for, say, 10 minutes. Come back just after past, and we can carry on. And for those who had their sweets stolen because I'm a softie, you are allowed. Oh, yeah. Oh, if you could return your counters up here when you have a moment, that'd be great, thanks. Did you watch the clip and then you knew what to do?
I seen it like way before,
Oh,
like years ago.
Sorry. Obscure British game shows. Not, I wasn't expecting people to know.
Is this part supposed to be, with AI, supposed to be, J instead? Because like this is our I,
Yeah.
and this is our I. If this is supposed to be IJ, then our I doesn't, it's supposed to be J. It's like
Yeah.
before.
I might have got my I's and J's confused.
Yeah, well, it's first, because this part is talking about, it's a, like, set a Nash equilibrium, therefore satisfies this.
Yeah, I think you're right. That would be JI.
Yeah,
Yeah,
there, okay.
it's part of the reason is because when I do, there's related sort of matrices in disease modeling,
Right,
and it's round the other way.
yeah,
It's the we talk about who infects who matrices,
Right.
and the rows and the columns are reversed.
Yeah,
Typically.
yeah.
So that was correct. This that should be a, let's see, on this here. Okay, I'll start up again. Quickly, the first one will come back. A couple of things. So first of all, you can tell I don't usually do evolutionary game theory because this is where I make mistakes. But there was a typo on this slide here. Thank you for pointing that out. This should have been a JI here rather than an IJ because we were saying a weak Nash equilibrium. There's a little typo there. And Javad just raised this question about this condition on this slide here, on slide 6. Really, it's all about whether this has to be true for all J or just the one that matches in the columns. So whether we need this to always be satisfied for all of them, or whether we need to have this only for AI J equal to AII. If there is some value of J that satisfies this, whether we need to do this for all J. It's a good question. I'm going to go away and double check that, and I will update the notes accordingly if it is different from this. It's something I'll have to sit down and think about. So I don't usually think about game theory. So I will update the notes if that is. It might be that either I've copied it down from the textbook incorrectly, or the textbook is correct, and I just need to get my head around it and make sure that I'm correct as I understand it properly. And or it might be that the textbook is incorrect. So I will update the notes accordingly and send out an announcement if it is different from what I've got written here. Okay. Okay. So the second part today, we're going to be thinking a little bit about mixed strategies to start with, and then we are going to go on to think about the repeated prisoner's dilemma. So it'll be like the scenario that we started with at the beginning, with the split and steal, a little bit related to that, but then thinking about what happens if you're going to repeat that process and play the same person again. Okay, so we've just found pure strategies. They're fairly straightforward to look at because we just need to look at the payoffs in the matrix, and then we can see, okay, well, because it's a pure strategy, then individuals are playing that strategy all the time. There's no sort of or rather the probability distributions are trivial because individuals are just playing them all the time. Mixed strategies, we have a non-trivial probability distribution, which we can describe by a vector. So a vector P could be a mixed strategy, and suppose it looks like this. P is equal to P1, P2, P3, if we have 3 possible strategies in our population. And there'll be some probability distribution of playing those strategies. So say 0.3, 0.7, 0. There's nothing special about those numbers other than they sum to 1. So this would correspond to play strategy 1 30% of the time, strategy 2 70% of the time, and strategy 3 never. Obviously, there's an infinite number of different probability distributions that we can come up with describing different mixed strategies. You recall as well from the last lecture that if there are only 2 types of individuals in the system, sorry, if there are only 2 strategies, then this is indistinguishable from, for example, if we had, let's call it Q is equal to 0.3, 0.7, if there were only those 2 strategies, this could be everyone plays strategy 1 30% of the time and strategy 2 70% of the time, or it could be 30% of the individuals always play strategy 1 and 70% of the individuals always play strategy 2. However, as soon as we go into more than 2 strategies, that second interpretation no longer applies. So it's easier to just think of these in general as being a probability distribution where everyone plays, everyone has the same probability distribution, say, and they play these strategies 30% of the time, 70% of the time, or 0. Okay. Okay, so in general, we want to also be able to find mixed strategies as well as pure strategies, but they are much harder to find. One of the things that we can do is we can kind of eliminate pure mixed strategies We can do that by thinking about something called the support of a strategy. So the support of a strategy P, which we'll call F of P, is going to be the set of all pure strategies that can be played in P. So we don't care at that point about their actual frequencies as long as, or their probabilities here, as long as they're above 0. So in the example above, F of P is just going to equal the set 1, 2. So strategies 1 and 2 can be played, but you don't play strategy 3. This then gives us a simple rule. It states that if P and Q are both ESSs, so P and Q here are just vectors describing different probability distributions. So if they're both ESSs, then we can't have the support of strategy P being contained in the support of strategy Q. That means that if we were to have mixed strategies, then as an ESS, then you wouldn't be able to have, there wouldn't be able to be any overlap in terms of the strategies that are contained within those mixed strategies. So for example, consider this payoff matrix, 4, 2, 1, 3. So first of all, before we go on, are there any Nash equilibria here? Yep. Okay. Strategy 1 is a Nash equilibrium. Why is it strategy 1 a Nash equilibrium? Yep. It's also an ESS, right? Because it's greater than 1 here. We also see that strategy 2 is also an ESS. So we have the pure strategies then for them P is equal to 1, 0 and Q is equal to 0, 1. But we can write any pure strategy in the same notations we write on mixed strategies. It's just a trivial probability distribution. So yeah, so in this case, no mixed strategy can be an ESS in this two-player game. Because any mixed strategy is always going to have both of these strategies within them, and therefore the supports are going to be the same. So we can't have them being an ESS. No ESSs in a 2x2 game. That's not going to be true in general if you had more strategies, right? Okay, let's go back to the prisoner's dilemma. So if you recall with our prisoner's dilemma, we had a payoff matrix that looked generically something like this. We call the entries A, B, C, D. And I'm just going to write in the columns here, sorry, in the rows and columns, headers, D's for defect and C for cooperate. D is equal to defect. C is equal to cooperate. We cooperate or collaborate here. So this is slightly different to the game you played because we have these strict inequalities here. Whereas you had the situation when you did your split or steal the sweets. If your opponent stole, then you always got 0, no matter what you did. So 2 of these payoffs would have to be equal. Okay, let's get you guys working this out. Are there any Nash equilibria in this game and any ESSs? Have a go at that for a minute. Okay, what do we think? Any Nash equilibria in this game? Did Oh, sorry, sorry. Okay, why is defect a Nash equilibria? Yeah, so if we think about, okay, if we look at each of our columns, then yeah, in this column here, A is greater than C. And then if we think about this column here, B is also greater than D. So it would always be the best thing to do. So D is a strong Nash equilibrium, in fact. And it is also an ESS. Since C cannot invade. So although D is greater than A, so the payoff for cooperators against cooperators is higher than defectors against defectors. Cooperator can't invade because I think most of the time it's going to be coming into contact initially when it's rare with defectors, and D is less than B, so it's going to be losing out. It's going to be less fit than the most common type in the population, therefore it's not going to be able to invade, even if it is the optimal strategy overall, if everyone did it. Okay, I'm going to try and bring us a little bit back into the realms of biology a bit more and thinking about the relevance of some of these games to biological scenarios. So I've talked a lot about ideas of cooperation and cheating. Sorry, the cable's a little bit dodgy. Ideas of cooperating and cheating, which obviously game theory links in very tightly, but I haven't talked too much about any specific examples. Hopefully that will stay in. One sort of model system that people study often is Dictyostelium. It's a genus of protists, or otherwise known as slime molds. Okay, and often here there'll be groups of. Sorry, I don't know why this is suddenly disconnecting all the time. Let's try and keep that steady. So these slime molds, they're very easy to study, and they're a classic example of cooperation and cheating. So what happens is these cells, they live independently, but then when conditions maybe change in the environment, maybe they run out of resources locally, maybe something, environmental stresses appear, they form something called a fruiting body. So this is a fruiting body here. So they group together, even though they're individuals, into these clumps of 100,000 or so genetically distinct individuals. So they group together to form this structure, and it rises up, and then they have this fruiting body at the top. So these cells have differentiated into these different cell types to make up the structure, either part of this stalk or part of this fruiting body. And the fruiting body enables sporulation and dispersal. So those cells can disperse, hopefully to areas that have more nutrients and things like that, more resources. And everything left on the fruiting body is left behind to die. So I think something like 20% of the cells maybe will survive, and 80% are sacrificing themselves. So this is a problem in the sense of why would individuals choose to be in this fruiting body? Shouldn't they just rely on others to build the stalk, and then they end up in the fruiting body, and then they can pass on their genes, and they're cheaters, essentially. They're not contributing to the public good of producing this fruiting body. Obviously, if everyone does that, then the whole thing is going to collapse and no one does anything. But evolution doesn't have that foresight. And so one of the things we often see is that, and this kind of links back to some of these ideas we talked about the other day with the hawk-dove game, that evolution doesn't do what is best for a population or best for a species. It does what is best for an individual. It doesn't have any foresight. It can't think about what's going to happen in the future. So what we can find sometimes is, we'll get onto ideas later in the course as well about evolutionary suicide, where evolution can drive populations extinct. So evolution is not always advantageous. So the question then is under what conditions do we expect cooperation to evolve? Sorry, I do not know why this cable has suddenly decided to die today. Okay. For some reason, the projector seems to have gone into calibration mode. It's okay. I will carry on talking anyway. Does everyone have the notes in front of them, just in case I can't get the screen back up? Okay. I'm going to try and go through this material quickly before it fails again. Okay, the point is there are some, it presents interesting problems about when do we expect cooperation to evolve. Game theory is one way of thinking about that process. I mentioned this idea of a repeated prisoner's dilemma. So one of the problems with the prisoner's dilemma game and a lot of the games we've been thinking about so far is that we're trying to adapt these ideas from game theory, which are about what happens if I come into contact and have, you know, one resource, what's going to be my expected outcome. But it's not really accounting for the fact that individuals may adopt strategies that depend on repeated interactions. So you won't typically just interact with that one individual once, or you won't encounter an individual with that strategy once. You would expect individuals and the genes that they carry, more importantly, to encounter each other again and again and again. And this could be within a single generation, or it could be over many generations when we're thinking about the genes that they carry. Okay, so we need to think about a much broader range of strategies and games where we have possibilities of things like retaliation or punishment. So depending on what had happened in the past, maybe you change your strategy. So you don't necessarily adopt the same strategy every single time. So this is an example of, this does happen in biological populations as well. So guppies are fish. And one thing they can do is they can cooperate to inspect predators. And experiments have shown that they punish those that don't participate in that sort of inspection of predators. So there's a slight risk, obviously, of trying to inspect a predator. You may be exposing yourself to predation. So individuals that don't contribute to that inspection, they are essentially punished by not being allowed to associate with the ones that do cooperate with each other. Okay, so even fish can retaliate. Remember that next time you go fishing or you're having fish and chips, if you're British. Okay, so what we want to do is we want to adapt our prisoner's dilemma game to allow for repeated interactions. And one of the things we can do for the payoff matrices is if we just go back a moment up to here, I just had generic values A, B, C, and D. One thing we can do is just rescale this. And rescaling it doesn't qualitatively change anything. So what I'm going to redo is I'm going to rescale this and call this new payoff matrix A hat. Again, it's going to be for defect and cooperate in our rows and columns like this. And all I'm going to do is I'm going to set my A value to be 0. It's a slight rescaling. The only reason to do this is just because it helps the analysis a little bit later on. So you still got the same conditions essentially as before, that B is greater than D and D is greater than C. And also here, we're going to have C has got to be negative now. Like I say, it doesn't change the dynamics of the game, but just helps to simplify the analysis a little bit. What we're going to do now is we're going to think about a probability R, the two players who are currently interacting with each other. So they're currently facing each other. They will meet again in another round in the future, with all rounds being independent of each other. Okay, so this would be like you guys pairing up as we did at the start, and then we do another round of that and you randomly choose another pair. What's the probability that you're going to choose that person again? Well, it would be 1 over the number of individuals in this room minus 1. You can't choose yourself. Okay, doesn't matter what that probability is R, how it's determined. We're just going to assume that there is a probability that they meet each other again. And so we can think about the probability that they meet each other n times. It's just going to be R power of n. This is going to be a simplified version as well, in the sense where either these organisms live forever, or we're just thinking about over a short enough period of time. Yeah, suppose they all live for the same length of time. How many times do they interact during their lifetimes? Okay. So we can think about the expected number of meetings they're going to have between two individuals who encounter each other at least once. Is going to be what? The expected number of meetings. Well, they've encountered each other once, so it's going to be 1. And then they encounter each other again. A second time is going to be probability R. And then again, probability r squared plus r cubed plus and so on. And anyone tell me what this is? Yeah, so we can just write L is equal to, okay, I'll do this in a different color so it doesn't get confused. L is equal to an infinite series R to the n. If you've forgotten how we solve these, one thing we can do is we can divide throughout by r. We have 1 over r plus 1 plus r plus r squared and so on. And because we're dealing with infinite series, this thing here is the same as this thing here. So L over R is equal to 1 over R plus L. Do a little bit of rearranging here. We multiply throughout by R. We're going to have L is equal to 1 plus LR. Subtract LR from both sides, and we'll get L times by 1 minus R is going to equal 1. Or L is equal to 1 over 1 minus R. Is everyone okay with this step, what I did here? Yeah? Good. Okay, so we know now what is the expected number of meetings that we're going to have for these two individuals who have met once. The question then is, what are our strategies going to be? And there's actually been quite a lot of research into this as to like what is the best strategy in a repeated prisoner's dilemma game, because it's kind of the archetypal game of cooperation. Lots of people have sort of tried to figure out, okay, what strategies can we play? So the problem now is that we have an infinite number of strategies that we can play, infinite number of different strategies, because we could you could base your strategy in the nth round on anything that happened in any of the n-1 rounds. So we've got an infinite number of strategies because we're meeting essentially an infinite number of times. Two common strategies that I talked about are always defect, which, as you might expect, is to just always play D, so always defect. When I say play D here, it just means that that's the strategy that you employ, regardless of what the other one does. Another one is tit for tat. And this is play cooperate first, play C first in the first round, and then copy what an opponent does. What the opponent did on last encounter. So tit for tat in the first round, you cooperate, and then after that, you just remember what the opponent did in the last round, and you just copy what they did in the last round. There's another common strategy, I can't remember what it's called now, but in that one, you don't have to remember what your opponent did. You just have to remember what payoff you received yourself. And then depending on the payoff that you received, then that informs whether you cooperate or defect. It's a slightly different version. Essentially, there's been various competitions to try to find what is the best strategy as a general principle in this infinite game. Okay, so using this information above and from the previous slide, what I want you to do is to construct a payoff matrix for the repeated prisoner's dilemma. So I want to have a matrix A, which has always defect against tit for tat. And I want to know what are the payoffs based on what we had on this slide here and this slide here. In fact, I'll write those things here. So our original payoff matrix for one interaction was 0, B, C, and D. And our expected number of encounters is 1 over 1 minus R. So have a go using that information to write down your payoff matrix for the repeated prisoner's dilemma. Okay, can I have a show of hands who's got that? Not sure? Yep. Okay. Let's go through each of these to make sure everyone's on the same page. Okay, so if you play always defect against always defect, well, in the first round, your payoff is going to be 0. In the second round, your payoff is going to be 0. In the third round, your payoff is going to be 0. And so on. An infinite sum of zeros here. Always defect, your payoff is always going to be 0. Okay, if you play always defect against tit for tat, what's your payoff going to be in the first round? B, yep. Okay, so you defected in the first round. What happens in the second round? What's your payoff going to be in the second round? Why is it going to be 0?
Because the opponent is going to copy what I did, which was that.
Yep, okay. And then the third round? Okay, we got zeros. Off to infinity there. Okay. So if you play always defect against someone's playing tit for tat, you get B in the first round, but then after that, you get nothing. What about if you do tit for tat against always defect? What do you get this time in the first round? It's bottom left entry. C, yeah. And then second round. Yeah, and then zeros. Carrying on. And then lastly, tit for tat against tit for tat. What do you get in the first round? Second round? Always D, right? Okay. So we can simplify this then as 0, B, C. And the question then is, how many Ds do we have? Well, our expected number of encounters is going to be L. So D times by L, which I'll just write as D times by 1 over 1 minus R. The risks seem slightly unclear here. These sums here are based on what you would get per round. This is not really a strict equals sign. This is the payoff matrix here, and think of this as just a sort of thinking what those infinite sums are. We then have to multiply those infinite sums by how often you're going to expect to come into contact with said individual. Okay, so this is our payoff matrix when we have an infinite series. The question then is, when is tit for tat in ESS? Is always defect in ESS? And what about if we sketch a graph of the payoffs? So I'll work through those. So tit for tat is going to be an ESS. If what? Well, let's have a look at this matrix up here. Well, we know for this to be an ESS that this entry here is going to have to be bigger than this entry here. And that the other strategy is not going to be able to invade it, right? So that means that we need D over 1 minus R to be greater than B. And B is also positive, so this deals with the 0 condition as well. So we have a condition based on our probability of future encounters and our payoffs, the original payoffs for one encounter B and D, to give us tit for tat being an ESS. Okay, how about always defect? Is always defect an ESS? And if so, when? Ideas? Remember that C in this rescaled game is negative. So always defect against itself is going to always be good, okay? So always defect is always an ESS since C is strictly less than 0. So it's a strict Nash equilibrium. It's an ESS. Okay, about the third part. Third part, we're going to be asked to sketch a graph of the payoffs for each strategy against the frequency of our always defectors. And I'm going to call this frequency of our always defect strategy P. So how do we work out the payoffs for each strategy? Well, when you think about what they're expecting to get based on their encounters with other individuals in the population. So it's the expectation for always defect. Well, if we think about their interactions with other individuals who always defect, they always just get 0 for those interactions. So they get 0 to their payoff times by the frequency of always defectors in the population, P. And then we have 1 minus P, the frequency of tit for tat players, times by what? Well, we learned above that their payoff for interactions with these individuals is going to be P. This is just B times by 1 minus P. My players who play tit for tat, we can do exactly the same thing. Just going to move these bits over here. So for these guys, when they encounter someone who plays always defect, then they get a payoff of C, which remember C was negative, so you have C times by P as their expected payoff for interactions with individuals who play always defect. And they get 1 minus P frequency of tit for tat players times by their payoff, D over 1 minus R. We can do a little bit of rearranging to get P times by C minus D over 1 minus R plus D over 1 minus R. And note that both of these are linear in P, and they decrease with P. So we can sketch a graph of the expected payoff as the frequency of always defect increases. So payoff. So let's look first of all at our always defect. So our always defect, their payoff is going to be B when no one else is in the population. So if there's only, sorry, if there's only tit for tat players in the population, they'll get a payoff of B. They get that in the first round, and then they get nothing else for any of the second rounds. And their graph will look something like this. And then we've got two possibilities here, depending on this condition up here. I'm going to assume that this is satisfied, that D over 1 minus R is greater than B. So if we have D over 1 minus R here, greater than B. And payoff for tit for tat will look something like this. It's my tit for tat. And this is my always defect. So in this particular case, we see that tit for tat is an ESS. So you think about ESSs on the diagram like this as being here. Tit for tat is an ESS because it has the highest fitness when it is at a frequency of 100%. So it's 1 minus P. So it's when it's at a frequency of 1 here. Tit for tat is the best. Always defect has the highest fitness, highest payoff when it is the only strategy in the population. Nothing else can invade. That's why we can see that both of these are ESSs. This is like that diagram I showed earlier of there being two mountains next to each other. One of these may be higher than the other, but they're both ESSs because they're very difficult to invade locally. You can't escape them. So they're attracting in that sense. So yeah, we see that by sketching this graph of our payoffs, we can see that TFT is an ESS as long as this condition is satisfied, and is true for some value P star. Yeah, any P less than that P star, our TFT is going to be able to continue spreading. It's going to have the highest payoff. Obviously, if our D over 1 minus R is less, if it was down here, for example, then we would have something that looked more like this. This was our D over 1 minus R. This is our other possibility. If this was less than B, then TFT is just never able to invade. T is not an ESS. Always defect is always the best strategy. So what does this tell us then? Well, in situations like these guppies, say, because of their repeated interactions with each other, they should be judging their actions, if possible, based on what other individuals do. So they could sort of always just not bother to inspect their, predators. But if there are enough individuals that do inspect and they play this tit for tat strategy, then that would be the best strategy to employ as well. So there's an element of punishment there in terms of they would not in terms of associated, but they wouldn't contribute in the future to helping those individuals. Okay, so it's somewhat analogous to this. Okay, that's about it today. We finished a few minutes early, that's fine. So we've explored these different strategies in terms of pure strategies. We've looked at mixed strategies. We've thought about iterated or repeated games, and they can tell us something, like I said, more informative about traits such as cooperation. And this idea of an evolutionary stable strategy, or ESS, is going to appear again when we look at another approach to phenotypic evolution. So I mentioned earlier adaptive dynamics or evolutionary invasion analysis. That tells us something about not only what are potential optimal strategies, but also how do we get to those optimal strategies? And what happens when we maybe reach a strategy that might look like it's optimal from afar, but when we get there, it might not actually be as good as we think it is. So we'll get onto that a little bit later in the course. We'll be thinking about how we actually have invasion and replacement of strategies, as opposed to just competing strategies, and then thinking about not exactly the process of evolution. We're just here at the moment with these games. One of the problems is that we're just kind of a very, very simplified version of evolution, where there are these strategies. We're not worried about the genetics at all, but we're also not thinking about the process of invasion and replacement of one strategy compared to another. We're just kind of jumping to the end point. Okay, so we will deal with those probably in a couple of weeks. We might get to it just before the midterm. Next week, we are going to be looking at some asymmetric games, which make things a little bit more interesting than these ones that we've been doing so far. So everything so far has been symmetric in the sense that you've had the same set of strategies available to you. and your opponents. But that's not always going to be the case. For example, males and females might not be able to have the same strategies because they are biologically different to each other. So we can think about asymmetric games next week, and then we'll be starting to think about what happens about this process of evolution. Okay. Other than that, have a good week. Homework 2 is now available, and see you next week.